Hi, Alan.
Hi there.
Hello, Alan.
Hi.
How you doing?
Not bad, thanks so much.
I thought I'd just fire it up early.
Yeah.
It is recording on YouTube, so afterwards, Sue normally reminds me anyway just to edit it.
Yeah.
Before we put it live. I'll pause the recording as well, so I'll put my little flag up here to remind me to record. There we
Right.
go.
Okay.
I'm just going to go and get changed as well and have a quick wee, to be honest.
Yeah. I hope I'm fairly presentable. But
You're looking good.
yeah, I'm going to be connecting my little Surface Pro to the television wirelessly.
Okay.
So it all says that there's Zoom, and Sue will be watching next door on YouTube. So I hope there's enough broadband. So we'll see how it goes.
Well, there's only one way to find out, isn't there?
That's right. Well, I thought we may as well.
Yeah, excellent.
My little Surface Pro doesn't have a connection to the, with an HDMI cable, but it can connect wirelessly. Yeah, so we'll give it a go. And I just thought we'd practice switching between my PowerPoint, because I want to do a demonstration of how to process various X-rays, most of which I've taken myself in the past.
Yeah.
And I just need, so I'll be breaking out of the PowerPoint and into this program and then going back to the PowerPoint. It's right at the end, so if it don't work, we just abandon the. Yeah.
That's fine. That's all right, isn't it?
So I'm going to move to where I'm going to sit with my blue background.
Okay.
Turn the telly on, and
I've made you co-host.
Okay.
My video's just gone off. Let me start that again. There we go.
I'm going to turn the telly on.
More information on how long disruption
Bear with me, it's noisy.
OCs are working really hard to deliver our mail on time, but these issues.
Wireless display. And then I've got to try and connect up to this one and then see how it goes. Settings. Connect to a wireless display. Connect. DigiHome. Oh, that looks good. That do. Should I tell you what? Bear with me. Your mouse. Try the PowerPoint and see what happens. That's looking good.
Excellent.
Say something, Simon.
Yeah, how's that?
Yeah, oh, it's coming through my hi-fi system as well, because it's going through the television.
Excellent.
So that's
good.
Yeah, I think so. And PowerPoint's on. I don't know whether you can see that.
Can't see that at the moment. You've got to share your screen.
So I've got to share my screen on Zoom then.
Yeah.
Right. So where am I? Where's Zoom gone? I've got so many other little windows open. Let's see if I can shut a few of these things, because I've got too many things open. And if I'm going to be selecting, I want as few open as possible. I think they're probably all on my yeah, do. I'm just wondering whether to open up a new. Yeah, I think I'm going to do that. I'm going to cut out actually, and so you might lose me for a second or so, and then I'm going to log back in. So you might have to connect me. So I'm going to close this, see what happens. Oh, I can still see you. Oh, that's good.
Yeah, still got you.
Good, excellent. So I want to get rid of, need that. I don't need the settings anymore, I don't think. Right. So if I share my screen, screen to PowerPoint slideshow, I'm hoping that's just the screen too. So yes, it is, I think. Share that. So you should now see my first slide.
Got it.
Got it? Good.
Yeah,
Okay.
I've got, left-hand side strip and then grey box. Is
Yes.
that right?
Now, how can I stop sharing on that now?
Just go on to your next slide, Alex. I've only got it on. I've only got that strip on the screen. Just
Yeah, that's all I've got on it.
No, it is. Put it on your next slide, just so we've got a full one.
That's your next slide.
Brilliant. Excellent. Excellent.
Okay.
Yeah.
So it's basically, I don't want to give away my title until we're ready to start.
Yeah.
So I just thought I'd stick that on, and people can scan the QR code and get the Facebook if they want to, and stuff like that.
Yeah, nice one.
Yeah. So I'll stop that or pause it.
Excellent. I just want to try something as well. I'm just going to try and create a poll on Zoom, just in case we ever needed to use it in the future. I've never done it before. So I'm just going to.
Yes, I've seen sort of creating polls.
Yeah.
But, I haven't done it before. Now, where can I stick my Zoom image? I need it out of the way. Otherwise, it'll cover my script. The other thing I'm going to do is to try and share our meeting controls. Where they go? No.
Can you see that on screen? Test poll.
Yes, I can. Yes.
Try and just answer one of the questions. Does it give you an answer? A couple of questions, lots and not much. Can you select one of those?
Right. I'm not sure how I do that because I'm on. Hold on. I'm not sure whether my mouse will extend to that.
All right. Okay. Not to worry.
Oh, yes, it is. Yes, it is. Here we go. What can you see? Lots.
Just answer one of those.
So click that. I'm not sure. I've clicked on the lots, but
all right. Okay. I wonder if, because you're co-host, it's giving you the results of the poll as well as as me, because I've got the results of the poll up. So perhaps it does.
I've got I can see percentages.
Yeah. It's the same then.
Yeah.
Well, okay. So if I then end it.
Okay.
And share results.
I'm just going to try switching to a different screen and see what happens. Will that work? It's not. Enter. Don't think that's working, is it? Let's see. You are screen sharing. So I probably have to end the, this is what I wanted to find out. So if I escape out of, oh dear, is this not working either? Let me see. Slideshow. From the beginning. See, I can't see my screen sharing thing actually, where it says because it's hiding the, this is what I wanted to find out. It's hiding.
Can you minimize the screen or just make the window?
That's what I'm doing. That's what I'm doing. I've got several things, right. I did connected to the DigiHome. I need to get rid of that. How can I get rid of that? I want to minimize it. No, it's just telling me I'm connected to my screen. Right. Here we are. It's this bit that I've got to end. Right. Here we go. That's it. Right. So that's got that ended. Then let's see if I. No, I've just got your test poll. Your screen sharing.
So I've got your, I take it's your screensaver, the woman running on the beach.
Yes, which is not what I want. So how do I share what I want to switch to?
What do you want to share?
It's the DICOM viewer.
Okay, so if you share screen and then select the window you want to share.
Yeah. Hold on. So I've got to do stop share. You are share. New share.
Yeah.
Ah, that's it there. Yes. So let's try that. Share. So I've got to do it on my other screen, on my television screen. No, I still got the test poll.
No, I've got it. Dicon.
Have you? All right.
Yeah.
Okay.
Yeah, you can close off that. You should be able to close off that poll, I think.
Yeah. Okay. So I'm not seeing it on the television. So I need to, in some ways, extend my screen, don't I, to my television. But the problem with doing that, I'm not sure whether the PowerPoint will work on that. Let me just see. So I need settings, don't I? Settings. Display. Come on, give me my display. Oh, settings there. Let's see what that says. I've got two. No, that's not letting. That's pinned. Unpin the toolbar. Right. No, so that's not doing that. Let me just see privacy accounts. Remote. Permissions, clipboard, display, multitasking. Where's my screen? Display. Duplicate or extend, that's what I want. So let's try extend these displays. Duplicate these displays. Right, so I've now duplicated the display, so you can probably see all my settings and things.
No.
Changes.
No,
You can't. What can you see?
Just you and me. So there's no screen.
All right. Okay.
Be careful,
So,
Alan. Just be careful what you show, because remember it's live on YouTube as well.
Yeah. Okay. I'm not. Yeah. I'm just sort of describing what.
Yeah, I was just thinking about your settings and things.
Yeah. So what I need to do is to do that. I'm going to just start my first slide again. Right, that's working. Now, so what are you seeing now?
Just us two, still no screen share.
All right, okay. So I need to go back to the Zoom meeting, and then I need to share my screen, and then I need to select screen 2. So now you should see the slide again.
Got it. Yeah.
First slide.
Got it.
Yeah. Okay. Now I need to go back up to here. Do. Yes, it might not be possible to do this, but
now's the time to try it. Give it a go.
Yes. So that's switched to Zoom.
Are you now fully retired, Alan? Just for the
Yes, I am. Yeah.
Are you still going in and doing an odd day if they want you?
No, I went in last week just to sort of hold someone's hand, but that was it.
Yeah.
Because I'm not practicing now.
Right.
Yes, I can't get that Zoom menu to switch screens very easily, actually. While I'm on PowerPoint.
Okay.
So I think I will probably have to end the PowerPoint and then come out of that and then switch screens, which might take a few seconds to sort of work out, as long as
That's all right.
people don't mind.
Yeah, they can.
Yeah. I've got a little strip saying meeting controls, but I can't get that pinned on top, I don't think. Presumably, yes, you're just seeing that. Right. Oh, here we are. New. I think I know I might go do it. A new share. Yes. Ah, right. Okay. So let's try this again. Share. Now, what are you seeing, Simon?
Okay, I've got the X-ray image. DICOM.
You have.
Yeah.
Brilliant. Okay. So then when I've done that, I need to go back to a new share and go back to the PowerPoint. Or that one. Which one is it do I want? There's two PowerPoint, screen 2, screen 1. I want to share screen 2, don't I? Not screen 1, because that's mine.
Mm-hmm.
And are you back to the...
Yeah, got it. PowerPoint.
Brilliant. Okay. Oh, that's working then. So that's how I do it. Okay. So I have to switch my own screen 1 first of all, and then yeah, I think that's working. Good.
Brilliant.
Yeah.
Excellent.
So I now that's what I needed to work out is how I
do
well, on your view, you can't see the Zoom menu, can you? It's not coming down because that's presumably just for me to see.
Exactly.
On the television, there's the first slide, and when I put my put my mouse pointer on the second screen, the Zoom menu drops down. Yeah, you can't see that, can you?
That's right. I can't see that. Yeah.
No, that's brilliant.
They won't be able to see it.
Pause share. So what happens if I pause the share?
So if you pause the share, it stays. What it enables you, this is how I use it. If I've got a PowerPoint showing, I'll pause the share, and then let's say I've forgotten what the next few slides are. I can look at the slides here.
Yes.
Without them changing on the screen.
Right.
See what I mean? So what I would do is if I'd go, let's say it was you and you weren't sure what was coming up, you'd pause the share on that screen, go forward however many slides you want to, then come back to that screen and resume screen share.
Right. Okay.
That's what it pauses it going out.
Ah.
It's a clever little thing.
Yes. Right. Display settings on the PowerPoint says swap presenter view and slideshow, which I don't want to do because I've got it right at the moment, or duplicate the slideshow. I probably don't want to do that either.
No.
So, okay. And I need to reset my, actually I can pause the PowerPoint, I think, or can I? Yes, that's paused. Go back to the beginning. Pause it again, just so I can keep an eye on how long I'm taking. I reckon about 50, 52 minutes, and then the DICOM will be about another 5.
Excellent. Yeah, that's perfect, isn't it? People can normally do an hour, can't they?
Are you able to take questions?
Yeah, we'll do questions as well.
So if you, we probably invite people to put questions, I don't suppose, in the chat somewhere.
Yeah, I'm going to invite them to do it. If they're on Zoom, put it in on the Zoom chat, or stick it in on YouTube.
And you can monitor both, can you?
Yeah. I've got them both up on here.
And then at the end, if you want to sort of pick a few, and I hope I can answer them.
Yeah, absolutely. I can.
I might not be able to, but
well, you can try. At least I can try.
Yeah.
Super. Okay. I'm just going to go and have a quick wee.
Yeah. Okay. So what do we do? Pause something, do we?
Yeah. I'll. What to do is I would leave your screen sharing there if I were you.
Yeah. Fine.
And then just stop your video and mute. That's what I'll do, and I'll be back in 5 minutes.
Stop my video and mute.
And mute.
Sorry.
Yeah,
Oh yeah, yeah. Sorry, yes.
you got it.
So I
Yeah,
need-
yeah.
yeah.
So like this, like that, and then I'm going to mute as well.
Okay,
And you'll
I
see
can't
me
see
muted. If you look at me, Alan, you'll see me muted.
Right. Okay. Yeah.
And I'll be back in 5 minutes.
Okay. Evening, Linda.
Hello.
What can you see at the moment?
Just three little windows. You, Simon with Justice Weather School app little signal, and that's it.
Right, so you're not seeing the starting screen. Okay. No. I'll not start that yet, but because Simon may want to introduce the talk, although I think it should happen at the same time. Let me just see. Let me just see what happens. It's a bit complicated, this, because the Zoom settings disappear.
Yeah, oh, yeah, there it is.
When I start sharing my screen, I will see what happens. There we go. Oh, yes, I can still see me and you.
Yeah.
That's okay. And you should be able to see something different now.
Yeah, I can see the logo.
Good. Earlier on, my mouse was able to go onto my second screen, and it's not doing it now.
Oh, posh second screen.
Yeah.
Hi, Linda.
Hello.
How are you?
All right, and you?
Good. Yeah, I'm all right. Thank you.
Mine.
Oh, was that you, Linda? You've terrible indigestion you've got there.
That's my Wookie. Oh, stop looking at me like that.
Excellent.
The other one, I think Alan's already heard her screaming. She's a squealy thing.
Oh, really?
Yeah, she's got a squealy bark.
Oh,
He's all sorts. Shut up. Just they've been asleep. It's only since I started talking. I'll definitely mute.
yeah, definitely sounds like. Is it she or he?
That's a he.
He sounds like he should be on Star Wars.
Oh, he definitely. He's yeah, that's nothing. He howls and all sorts.
Excellent. Well, at least we're watching, Alan, and we've got Mum's watching, as well, and Sue will be watching.
It's funny, Simon, my mouse won't extend to my digital display, so that I can change the screen sharing. It was earlier, but it seems to have stopped now. I'm wondering if it's because I've got to select a different screen, but I'm not sure.
Odd, isn't it?
It's these screen settings that are confusing, isn't it? Select a display to change the settings for it. Drag the displays to rearrange them. I want 2 above.
Don't stop messing with
Try that. No. Yes, it's a bit weird, this. Earlier on, my mouse would go off my computer and then onto the second screen. It says extend these display, identify. This is screen 1 and that's screen 2. Yes, okay. Duplicate these displays. I think that's probably what I had, maybe. No, screen sharing is stopped because the external display is disconnected. Okay. Well, I don't really want to do that. So duplicating doesn't work. It has to be extension, doesn't it?
Yeah.
I think. So let's go back to my PowerPoint and then see what happens. Well, I can see my PowerPoint, but I can't see the Zoom imposed on it. Oh, I've stopped screen sharing. So what are you seeing? Just my background, are you?
Yeah, just got your background. Yeah.
All right, or me rather, on
Yeah.
my background.
Yeah.
Yes. Okay. So yeah. So I better start sharing again, haven't I?
No, I'm not going to record on Zoom, Alan. I'm going to let it do it on YouTube.
Yeah. Okay.
Yeah, might as well. There's no point in recording on both.
There we go. Yeah, we'll just have to wait and see what happens towards the end, Simon. But
Okay.
most of the talk will have been done.
Yeah. Okay. Okay. That's fine.
Are you going to introduce me? And
Yeah, we'll do. Yeah, I'll do all
yeah,
that.
okay.
I suspect this is probably the only meeting we're gonna have to do like this with any luck. I think we'll
Yes.
we'll be out of it, doesn't it?
It looks like.
Yeah. Mind you, I think the government's being a little bit prematurely optimistic.
Oh,
but,
yes.
never mind.
Yeah.
I think that might be more to satisfy backbenchers than anything else.
I
It?
think so. To hide
Yeah.
what else is going on.
Yeah. What a suggestion, eh? What a suggestion. Shocking.
Mm.
Well, I expected to see a few more up on Zoom.
Yeah.
Was Philippa coming?
Can't remember.
I think Philippa said she was.
I thought so.
Yeah. And John. John's normally on.
Now, why isn't my laser? Oh, I'm paused, aren't I? That's why my laser won't work. I'm just going to set
Okay.
this off and see whether my laser pointer works.
Okay. Did you click on the link in the email, Linda?
Yeah.
Oops, no, I don't want to do that.
Yeah.
Go back. I want the laser, pen, highlighter, ink.
Yeah, I did the
color.
latest one that you sent.
Yeah.
Mm.
It should have been all the same.
Oh,
I
it's
see.
Philippa.
Same link.
Mm.
That is Philippa.
It's Philippa. Oh, and she's gone again.
She tried.
Can you see the laser pointer on
Yeah,
there?
yeah, we got that, Alan. Yeah, I
Yeah.
can see that.
I have to use my fingers on my touch screen. Can't use the mouse.
Okay.
So I think what I'm going to do, I'm possibly going to get rid of this mouse. Actually, it's Sue's mouse I'm using, but I don't usually use a mouse. I'm going to try my touch screen, see what happens with that. No, I don't want to do that. Go back.
Is it voice activated as well?
Not quite, no. Arrow options, automatic, visible, hidden. What does that mean?
What
Ink
options?
color. It says on the pen symbol of the PowerPoint, where you can choose laser pointer, pen, or highlighter.
Yeah.
It's got arrow options, automatic, visible, or hidden.
All right.
Yeah, don't know what that is.
Not sure what that is. Is it automatic? It comes on when you wibble it across the screen.
Possibly, yeah. But when I've been, yes, it's not doing the mouse pointer. I can do it with my fingers.
Yeah.
Oh, that's all right. I'll just have to drag it with my fingers. That's all right. That's working all right.
Hi, Philippa.
Hi, Philippa.
Well, there's 9 of us.
Yeah.
10 of us. 11 of us.
Oh,
9:31. We better get started then.
I'll give it, Alan. Just give it a couple of minutes. Just in
Okay.
case
Yeah,
people
fine.
to get it on. Might as well, because there's a delay
Yeah.
on you. There's a delay on YouTube as well,
Okay.
so it might be worthwhile just giving it a minute or two. I think,
I'll go mute.
if that's okay.
Let's see if the Zoom works.
Okay.
Oh, it makes things disappear.
Yeah, it's gone.
I'll switch the Zoom off. There we go.
Okay. I think we should get started if you're happy, Alan.
Yeah.
Yeah. Okay.
Okay. Have you got to do your recording or restart it or whatever?
Just make sure everything's recording. Yeah. So we're recording on YouTube.
Okay.
I think that's how to do it. I'll tell you what I will do. Actually, I'm going to record as well.
You can hear me loud and clear?
Got you. Yeah.
Good.
Well, good evening, everybody. Thank you for joining us for this evening's meeting of Wombourne District Scientific and Historical Society. It's nice to see you here. Hope that you and yours are well. And with any luck, we're on the downward trend of Omicron, and perhaps we might be able to meet together again next month. If you're watching the recording of this, it might be next month already. We may be all meeting together already. Then again, we might not be. You'll know if you're from the future. But anyway, it's great to see you here this evening. Thank you for coming along. We've got a great talk this evening from our very own Alan Stevens, who, as well as being secretary of the society, is actually now a retired vet. And I'm sure Alan will tell us a little bit more about his background as well, just to fill in those of you who don't know Alan. But Alan is a great supporter of the society and has been a member of the society since day one, and indeed its secretary since day one as well. So Alan will be with us shortly. As I said, we are hopeful that we may be able to meet together next month, which is the 17th of February. That's Thursday, the 17th of February. And we'll be meeting in the community centre at 7:30 on that day. Still to confirm a speaker for that day, because we've been doing these a month at a time, not knowing whether we were going to be meeting online or in person. So we're still to confirm a speaker, but of course we'll let you know as soon as possible on that. And hopefully we can then get a full programme in place for you going forwards from that. March will be our AGM. So as I say, again, fingers crossed, we're going to be meeting together for that. And it'll be the first time we've been able to get together for the AGM for a few years. So if you're not a member of the society, you're more than welcome to come along to both the February meeting and to our March AGM as well. And who knows, you may want to join for the bargain price of, at the moment, £10 a year for all of your talks. So it'll be great to see you there for that face-to-face meeting. And I think that's all from the parish notices this month. As I say, the most important thing is that our meeting next month is on Thursday, the 17th of February. Okay, then, without further ado, I'll hand you over to Alan Stevens, who is going to present tonight's talk. Alan, it's all yours. Take it away.
Thank you, Simon. Okay. I can't see myself, but hopefully I don't need to. Anyway, good evening, everybody. Welcome to our Wombourne Scientific and Historical Society presentation. And yes, I'm sorry, it's not a live event. Tonight, I'm going to start on a journey, taking you to a place called Imagination, where we will encounter some interesting discoveries and advancements in the history and science of diagnostic imaging. So, part one, introduction. Imagine you have an object or body in front of you and you want to see into or through it. You want to know how it works and what is inside it, or find out what is going wrong with it. How could you do that? What problems would you need to solve to do that? You don't want to take the object apart. You don't want to cut the animal or person or object open. So you need something to get into the object, or for some of that something to come back out or pass through. And then you need to require something to see or collect what passes through. And you require ways of making sense of this collected information. I'm planning to do a series of talks, which I hope will shed some light on this. And talking of shedding some light, maybe we could use a very bright light and use that to illuminate the body. Very eerie, isn't it? What can you see? So being able to see into or through an object or body and work out what is going on is one of the goals of science. It's one of the goals of science fiction, and it's been featured in literature throughout history. Perhaps we could phone some friends or who may be able to help, or better still, let's beam them aboard. Here are just 3 of the many Star Trek doctors. You know, I had to get Star Trek in there somehow, didn't I? That have made their mark over the years. So from left to right, we've got Dr. Catherine Pulaski, Dr. Beverly Crusher, and Dr. Leonard Bones McCoy. And this was one of the many devices that they used to find out what was going on in their patients, some of whom were as strange as some of my veterinary subjects, like this one, if I can point him out. Oh, sorry, beg your pardon, let's go back again. Is my, no, that's not working very well, sorry about that. Technical issue. Get them back in, we keep beaming them aboard. Sorry, my laser pointer isn't working, but you can see the guy on the bottom left there. I've forgotten what breed of person he is. But anyway, this is a medical tricorder. And the medical tricorder was a specialized version of the standard Starfleet tricorder. It was equipped with sensors and analysis software tailored for medical diagnostic purposes. They were usually the first tool a Starfleet doctor utilized when assessing a patient's condition. Medical tricorders could function aboard ship, in sick bay, as well as on away missions. I'm not going to try and explain how it works, but it's an excellent concept. And here it is in action. Dr. Beverly Crusher and her associates giving aid to a recumbent Captain Jean-Luc Picard. Maybe he had just one too many Earl Grey teas, enjoying the New Year celebrations too much. And somehow the information from the tricorder gets from the tricorder onto one of the medical wall displays, which told them all they needed to know. Brilliant. So I plan to carry out a series of 4 talks or presentations about imaging. I'm going to limit my talks to considering mainly diagnostic imaging from a medical or veterinary point of view, but application of some of these techniques go well beyond the boundaries of medicine, including physics, chemistry, engineering, and even national security. So we're going to talk about the X-ray, its derivative. Not, these aren't for tonight, by the way, don't worry. The derivative CT or computed tomography, and I'll explain that in the next talk or in another talk. We'll possibly touch on gamma scintigraphy, because all of these have diagnostic and interventional applications. Then there's ultrasound, which has therapeutic and diagnostic uses. And then hopefully, if I survive that long, MRI, purely diagnostic. With these technical advances, all of these imaging modalities can be used for diagnosis, but also some of them can be used to actually do surgery or interventions in real time. So this is my part 2, the X-ray machine, and we'll concentrate on that tonight. So returning to our earlier slide showing the requirements of our imaging devices, let's apply this to our X-ray machine. Our first requirement are X-rays and something that makes X-rays, an X-ray generator. How will we see or collect the results of what passes through? In the early days, even up to the end of the last century, it was analog photographic film. Modern systems use laser scanners to extract the data, just like scanning a photograph, or directly pass the data from X-ray sensing materials into computers. We'll talk about that later. And then what do we do with the collected information provided by these X-rays so we can answer our question, what is going on here? The light box or film viewer, but nowadays computers are used to assemble and send that information to a computer monitor. So we'll go back in time, first of all, and look at the history and discovery of X-rays. And our story starts with a couple of scientists. The first one was English physicist William Crookes. He was a pioneer of vacuum tubes, inventing the Crookes tube, which was made in 1875. This was a foundational discovery that eventually changed the whole of chemistry and physics. This became the cathode ray tube, which was used in televisions and X-ray generators and oscilloscopes. And the next person is Röntgen, Wilhelm Conrad Röntgen, if I pronounce that correctly. During 1895, at his laboratory in the Würzburg Physical Institute of the University of Würzburg, Röntgen was investigating the external effects produced when one passes very high voltage electrical discharges through various types of vacuum tubes, vacuum tube equipment. Apparatuses from Philip von Leonard, William Crookes, we've just talked about, Johann Hittorf, Heinrich Hertz, and this one will ring a bell, Nikola Tesla. The equipment that Röntgen and others used to generate these high voltages was the Ruhmkorff coil. Sorry, these are difficult things to say. The Ruhmkorff coil. This is basically a transformer. The first tube he used was the Leonard tube. In his experiment, Röntgen added a thin aluminium window labeled B. I hope you can see that on the top right of the top image. Sorry, I'll try and point it out with a laser pointer, but it wasn't working earlier. Oh, there we go. Can you see that there? That's point B to permit the cathode rays to exit the tube. So you can see them coming out here. And also a cardboard covering, which is not shown in this drawing, to protect the aluminium from damage by the strong electrostatic field that produces the cathode rays. Röntgen knew from previous experiments that the cardboard covering prevented visible light from escaping. Yet he observed that the invisible cathode rays caused a fluorescent effect on a nearby cardboard screen painted with barium platinocyanide when it was placed close to the aluminium window. The next tube he tried was the Crookes tube. It occurred to Röntgen that the Crookes tube, having a much thicker glass wall than the Leonard tube, might also cause this fluorescent effect. So this was his experiment. In the late afternoon of the 8th of November, 1895, Röntgen was determined to test his idea. As before, he carefully constructed a black cardboard covering similar to the one he had used on the Leonard tube. He covered the Crookes-Hittorf tube with this cardboard covering and then attached the electrodes to the Ruhmkorff coil to generate an electrostatic charge. Before setting up to test his idea, Röntgen darkened the room to test the opacity of the cardboard cover. As he passed the Ruhmkorff coil charge through the tube, he determined that the cover was light tight, and so turned to prepare the next step of the experiment, which was to check for cathode rays with the barium platinocyanide screen. But before he could do that, Röntgen noticed, sorry, I lost my place. Yes, he noticed a faint shimmering from a bench a few feet away from the tube. To be sure, he tried several more discharges and saw the same shimmering each time. Striking a match, he discovered the shimmering had come from the location of the barium platinocyanide screen he had been intending to use next. Röntgen speculated that a new kind of ray, different from the cathode rays, might be responsible. 8th of November was a Friday, so he took advantage of the weekend to repeat his experiments and made his first notes. In the following weeks, he ate and slept in his laboratory as he investigated many properties of the new rays. He temporarily termed X-rays, using the mathematical designation X for something unknown. The new rays came to bear his name in many languages, Röntgen rays, and the associated X-ray radiograms as Röntgenograms. Try and say that when you've had one too many. At one point, anyway, he was investigating the ability of various materials to stop the rays. Röntgen brought a small piece of lead into position while a discharge was occurring. Röntgen thus saw the first radiographic image, his own flickering ghostly skeleton on the barium platinocyanide screen. He later reported it was at this point that he decided to continue his experiments in secrecy, fearing for his professional reputation if his observations were in error. The first radiographs. About 6 weeks after his discovery, he took a picture, a radiograph, using the X-rays of his wife, Anna Bertha's hand. When she saw her skeleton, she exclaimed, "I have seen my death." He later took a better picture of his friend, Albert von Kurlicher's hand at a public lecture. His discovery was published in German on 28th of December 1895 and in English the following month. In the article, Röntgen noticed that X-rays penetrate different materials to a greater or lesser extent, remarking on the difference between bone and flesh, and that images could be captured on photographic plates. How does that compare with my illuminated hand? So, what are X-rays? An X-ray is a penetrating form of high-energy photons. They are part of the electromagnetic spectrum. X-rays are invisible. So going from right to left, we have the radio waves, microwaves, infrared, and then the only part of the electromagnetic spectrum that we can see, and hence the visible spectrum, merging to ultraviolet, and then we get our X-rays, and lastly gamma rays. And as we go from right to left, this is at the the middle numbers are just below the scale. As we go from right to left, the wavelength shortens, and at the top there, the frequency increases. And the velocity of all of these radiations is constant. It's the speed of light. Electromagnetic type ionizing radiation extends from the extreme ultraviolet. I'm not sure whether I can point this out. I'll try with my little pointer. Is that coming on? Oh, yes, it is. There we go. From the ultraviolet all the way up to here. All of these will ionize tissues or objects. So X-rays and the gamma rays and the ultraviolet all ionize. These high-energy photons are able to cause electrons to shift to an outer orbit around the nucleus of an atom, or completely knock an electron off the atom and the molecules, causing ionization, so they become positively charged. And they're also capable of causing the most severe types of molecular damage, which can happen in biology to any type of biomolecule, including mutation and cancer, and often at great depths below the skin, since the higher end of the X-ray spectrum and all the gamma ray spectrum penetrate matter. So how are X-rays produced? So we saw earlier how one spin-off of the Crookes tube was the production of X-rays. So I'll try and give a simplified explanation of how they're produced, but the full details of the action in a Crookes tube are complicated. This is because although there is a partial vacuum in the tube, about 1/1,000,000 of an atmosphere, there is a non-equilibrium mixture or plasma of positively charged ions, negatively charged electrons, and neutral atoms. And these are constantly interacting. And this causes a glow discharge, a pattern of different colored glowing regions in the gas, depending on the pressure in the tube when the tube is charged. I could probably do with the help of our member Will Townsend to explain what's going on, as it involves quantum mechanics. So here's our Crookes tube, and it's made of glass, and inside there's a partial vacuum, and there's no heating element in Crookes tubes. They're called cold cathode ray tubes, making them different and less efficient than the modern X-ray tubes. Electrons are generated by the ionization of the residual air by the direct current voltage of a few kilovolts up to 100,000 volts applied between the cathode. Is that working? No, oops, sorry, beg your pardon. Let's go back again. I'll try my pointer again. That's the cathode there, and then that's the power supply, and then the anode is here. So electrons are generated by the ionization of residual air by high direct current. And we saw that a few slides ago, the whole setup. So when the voltage is applied to the tube, an electric field accelerates the small number of electrically charged ions and free electrons always present in the gas, created by natural processes like photoionization and radioactivity. The electrons collide with each other, with other gas molecules, knocking electrons off them and thus creating more positive ions. And the electrons go on to create more ions and electrons in a chain reaction called a Townsend discharge or avalanche. I told you we needed our friend Will. He's got a method or an effect named after him there. I don't think it's named after Will though. Not only is this avalanche happening in the direction of cathode to anode, but there's an equivalent avalanche going in the opposite direction from anode to cathode, because all the positive ions produced by these electrons collisions are attracted to the cathode or the negative electrode. And when these ions strike the cathode, they knock large numbers of electrons out of the surface of the metal, which in turn are repelled by the cathode and attracted to the anode or the positive electrode. So these are the cathode rays, and they create a glow discharge, a pattern of different colored glowing regions in the gas, depending on the pressure in the tube. So when enough of the air has been removed from the tube, most of the electrons can travel the length of the tube without striking a gas molecule. The high voltage accelerates these low mass particles to a high velocity, about 37,000 miles a second, or 59,000 kilometers a second. That's about a 20% of the speed of light for a typical tube voltage of 10 kilovolts. And when they get to the anode end of the tube, they have so much momentum that although they are attracted to the anode, many fly past it and strike the end wall of the tube. And when they strike atoms in the glass, they knock their orbital electrons into a higher energy level. And when those electrons fall back to their original energy level, they emit light. And this process is called cathodoluminescence. And it causes the glass to glow, usually yellow-green. And the electrons themselves are invisible, but the glow reveals where the beam of electrons strike the glass. Later on, researchers painted the inside back wall of the tube with a phosphor, a fluorescent chemical such as zinc sulfide, in order to make the glow more visible. After striking the wall, electrons eventually make their way back to the anode, flow through the anode wire, the power supply, and then back to the cathode. The clear shadow of the cross shows these early pioneers that electrons were traveling in straight lines. So the modern X-ray tube. We're going to jump forward 100 years or so and look at modern X-ray tubes. As X-ray generators developed, modifications were made which improved the production of X-rays and improved the longevity by using heating elements to produce electrons and shaping the anode to deflect the X-rays in a controlled manner. The anode was prone to wear or burn out, so a target was made of tungsten, non-rotating in cheaper machines, but rotating to spread the load on the anode and distribute the wear and tear. So the top left shows a tube with a heating element, which can I show you? Yes, there it is there. Okay, that's the heating element. And that's colored orange, and a static angled anode, which is colored blue. Whoops, come back here. Whoops, we're going the wrong way. This is the trouble when you use your finger. So is that working? No, it's not working, my laser pointer. Sorry about that, folks. Anyway, you can see the blue angled anode there. And to keep the tube from overheating, it's surrounded by an oil bath. And the whole setup is encased in lead to prevent X-rays being emitted in any but the desired location or direction. And this is now a compound rotating anode X-ray tube. And you see a lot more complicated. It has a circular molybdenum neck and base and an embedded tungsten target ring. And this is a close-up of that tungsten ring, and you can see there's some concentric circles at the bottom, and then in the middle of them there's lots of pitted areas, and that's where the electrons are striking the tungsten and generating the X-rays. And this is a sort of a cutaway model of someone being X-rayed, and these X-rays are hazardous, and we need to prevent unnecessary exposure. Can you see the structure between the tube and the patient? That's a collimator, and I'll look at that part in a while. But first we'll digress to look at the historical use of X-ray machines and then look at some newer developments. So there are two examples of very early X-ray machines. The first one on the right is Canada's first X-ray machine, and notice that there's no cooling devices nor any lead shielding to protect the machine operators or the patients they were used on. From a veterinary point of view, veterinary surgeons were no slower to realize the potential of Röntgen's rays. The discovery featured often in the 1896 volume of The Veterinarian. In the March edition, the editor observed, how we should all welcome the new photography's application to veterinary medicine. A few lines later, however, the mood was dampened. We are afraid our patients would not make good sitters. Although this did seem to cause some delay in the veterinary use of X-rays, the same journal published the paper, The Röntgen Rays in Veterinary Practice, in the September of 1896. The article, co-written by the then principal of the Royal Veterinary College, Professor Frederick Hobday, recounts radiographic experiments on both living and dead horses, dogs and cats, with and without anesthesia or sedation. And the article concluded that the Röntgen rays can be successfully applied to the smaller animals without much difficulty. In the horse, the mechanical difficulties of restraint have been successfully overcome. To penetrate easily through the thicker portion, of course, requires greater power than is at present available, or else a prolonged exposure. The final paragraph gives a practical note on the diagnostic use of both negative and printed X-ray images. So let's have a look at some variations of the theme, some newer developments. All of these machines, except the wall-mounted dental machine on the bottom right, are portable to some degree or other. One on the top left is a typical modern hospital portable X-ray machine. And then there are, on the top row, there are two X-ray machines that look like cameras. There's no film in them. All they are is an X-ray tube, which is battery powered. And a similar one on the bottom left, which look like hair dryers. The batteries are in the handle, and that they are very useful for taking X-rays in difficult positions or situations. Very good for doing dental X-rays, and they are very good also for X-raying out in the field. But you still have to do something with the image that you produced on the plate, and we'll look at that later. So what next? We've made our X-rays with the X-ray tube. How do we control them? They are dangerous to living tissues. We need to direct them to where they are needed and prevent them having any unwanted actions. To explain this, I'm going to take a more detailed look at a modern X-ray unit. Now, similar to a camera, we can control the exposure or the quantity or quality of the X-rays by controlling the milliamps and the kilovolts. I'll see if I can get my mouse working again. Oh dear, sorry, I beg your pardon. Let's go back again. I'll try the laser pointer again, but I'm not sure whether it will work. So the milliamps are here. Okay, that's 100 milliamps. Kilovolts here is, I think, I can't really read that, whether it's 12.5 kilovolts or 125 kilovolts. We usually take X-rays at about 60, 70 kilovolts. So this, I think for a human, it could be 125 there. And the milliamperage, which is here, that controls in the middle, that controls the heating filament. So the more heat equals more electrons. And the kilovolts control the acceleration of the electrons. More speed equals more penetration, but also more scatter, which can cause a blurring or fogging of the final image. The power supply is either main supply or batteries for handheld machines, or a dedicated power plant for the more powerful static machines. And then the third element is time. This is the time that the current is applied to the heating filament, which produces the electrons. This is very short, so it's measured in milliseconds. Often the milliamps and the time are combined as milliamp seconds. And you can see that on the display there on the right-hand side. Modern machines are programmed so that you can select the patient or animal type, the part of the body you want to image, and the machine will provide the exposure factors to give you a reasonable image. Collimation. X-rays are produced from a small point source in the X-ray generator and fan outwards. The most useful X-rays are those which come from the center. So a lead aperture is used to absorb the peripheral X-rays, and this is termed collimation. And modern machines have what's called a light beam diaphragm. And a light beam diaphragm contains the collimation. It's seen in these machines. Again, I'm not sure whether my pointer will work. It'd be nice if it did, and I can point them out. So that's the light beam diaphragm in that machine, here in that machine, and here in that little box down here, at this end here. And these control the lead shutters here, here, and up here. It's two controls which control the lead shutters. And the area to be eliminated is illuminated by a light, hence the name, the light beam diaphragm. And the center point of the image where you're aiming at is shown by shadowed crosshairs or by a laser pointer. As I mentioned earlier, the more X-rays you produce, the more can scatter in all directions when they hit the object. So on the left-hand side, you can see the X-ray tube. The object is just an oval dotted line. And below that is a thing called an X-ray grid. And then below that is the film cassette of various sorts, either computerized or photographic. But because the X-rays bounce off at different angles, this is called scatter. And the X-rays can rebound even off the table or the X-ray cassette if made of the wrong materials, or you put a bit of metal on it, or missing a layer designed to absorb these stray X-rays. And this is called back scatter. If you remember polarizing sunglasses, they were very effective at blocking light scattered when reflected off a rippling water surface. And that's similar to how a grid works. So they're made of parallel strips of high attenuating, that's blocking material such as lead, with an interspaced filling with a low attenuating or low blocking material such as carbon fiber or organic spacer. The strips can be orientated either linear or crossed in their longitudinal axis. As scattered radiation is increased in thicker patients and at larger field sizes, grids are useful in such scenarios to improve image contrast. The downside can be that the grid lines can be seen on the final image, which may obscure some detail. And the other downside is you need more X-rays to be in the first place, a higher exposure to give you the same X-ray image as one without a grid. So, but grid lines can be eliminated by moving the grid at right angles to the grid lines during the exposure. If the range and speed of the motion is sufficient, the grid lines will be blurred out. The motion may be oscillating, vibrating, or reciprocating, and must be continuous and smooth, and the motion must also begin before exposure and continue after exposure. This is a modern X-ray table with a built-in grid and cassette holder. At the moment, it's not in position, but when you're ready to take the picture, you push that drawer back under the table and it's ready to take the X-ray. So we met our first requirement. We've made our X-rays, we've tamed and controlled them, we've projected them at our patient. Our second requirement is to see or collect those X-rays which pass through. So how shall we accomplish this? In the early days, even up to the end of the last century, it was analog photographic film in light-proof cassettes. Modern systems use laser scanners to extract the data, just like scanning a photograph. That's computed radiography. Or the third way is to directly pass the data from the X-ray sensing materials into computers, and that's called direct digital radiography. So we're going to look at the first method, photographic film and intensifying screens. On the left is an empty plain cassette, basically a light-proof box with a metal screen to absorb any remaining X-rays. Direct exposure by X-rays will produce an image, as we saw earlier with Röntgen's friend's hand, but the dose is massive compared to the setup on the right. This isn't good for patient or the X-ray machine. But on the right is a cassette with intensifying screens, and these are coated with fluorescent crystals called phosphors, which glow when any X-rays passing through the patient strike the screen, resulting in photoluminescence. This amplifies the strength and effect of the X-ray stream by 25 to 400 times, but the light emission produces a blurring effect. The light photons expose the silver halide crystals in the X-ray film emulsion. When developed, these exposed crystals turn into black silver. So the more X-rays that pass through, the darker the image. The original intensifying screens used to be made with calcium tungstate, which fluoresce with a blue light. In the 1980s, rare earth screens were available, and these were more efficient, emitting a green fluorescence. So green sensitive X-ray film had to be used with these screens. The rare earths were gadolinium, lanthanum, and yttrium. In the middle is a cross-section of the cassette loaded with film. This is effectively like a sandwich. In the middle, which is coloured grey, sits the film. Either side of the film are intensifying screens, each with its protective coating and phosphor layer next to the film. The reflector, the green line, makes the screens more efficient. The pressure pads keep everything flat and sandwiched together. And then the top layer is plastic and allows the passage of X-rays, and the bottom outer layer has a lead backing which absorbs any X-rays which have passed through to the bottom of the cassette, preventing backscatter. And then when you've taken your X-ray film, you've got to develop it. In a busy veterinary centre of the last century, doing radiography was a chore. The correct exposure had to be worked out for each species, from a 3-kilogram Yorkshire Terrier to a 60-kilogram St. Bernard or a 100-gram hamster. So complicated exposure charts were created by more or less by trial and error. The receiving medium was sheet film, which had to be handled carefully to avoid scratching, and placed in a light-proof cassettes in a darkroom. The cassette was placed under the patient, given the best guess exposure or one from the exposure table. Then the plate was taken back to the darkroom, the exposed film removed from the cassette and developed by hand, passing through a developer tank for 4 minutes, a quick dip in a wash tank, then minimum 2 minutes in a fixing tank, and then the final wash tank. At that stage, the developed film could be looked at, but the gelatin-like emulsion with the metallic silver image was still wet and more easily scratched, until it was fixed for a further time and then dried. So adding up all this took a minimum of 8 minutes per X-ray. One could, of course, process up to 3 films at a time, but extra care was needed to prevent scratches. So, providing the patient had kept still, providing the exposure factors were correct, providing the developing chemicals were at the optimum temperature and not degraded by overuse, you could end up with a reasonable diagnostic image. Then, for each area of interest, you had to take additional views at different angles to the first in order to build up a pseudo 3-dimensional view of the area. And then what do you do with all these films or photographs? They had to be stored in such a way that they could be found again when needed. The number of films that got misplaced or lost was legion. There must be a better way. So along came the wet film autoprocessor. This type of machine certainly helped to speed up the processing of the films, but wasn't ideal because the machines needed a lot of maintenance, especially if under or overused. One still had the problem of storing or filing all the films. There must be an even better way. Welcome to the computer. So wet film processing had been around for over 100 years. It still is used in some places, but all hospitals and many veterinary practices have switched to either computed radiography, which I would describe as the even better way to see and collect what the X-ray machines have sent through to the patient, or, and this is the bee's knees, but also the most expensive and the most demanding as far as computing resources are concerned, is direct digital radiography. And these are both digital imaging modalities that create images very quickly. And these images can be viewed, manipulated, and optimized to provide the best diagnostic information for the clinician, and can be permanently attached in a lossless manner to the patient record, which is then stored on the computer. And not only are the images stored, they can be retrieved easily, transmitted to other clinicians for second or third opinions, printed out as a hard copy if needed. All in all, a win-win situation. To explain these advanced methods is complicated, so I shall only provide a little detail, but even so, you will see for yourselves how the clever use of computers lasers, ultraviolet erasers at various stages can complete the task. Have we fulfilled the Star Trek dream? I'd say we're getting closer. So let's start with computed radiography. So you have at the top there the CR plate. So instead of a cassette containing intensifying screens and X-ray film, we now have a cassette which has an opening along one end or one side. It still retains the top surface transparent to the X-rays and the bottom surface incorporating a lead layer. But instead of film, we have a barium fluorohalide plate, often referred to as a phosphor plate. Unlike film, this plate is reusable thousands of times. The crystals within the plate are excited during radiation exposure. Electrons jump to color holes in the conduction band of the plate and remain there, creating a latent image. When the X-ray has been taken, the cassette with its plate is inserted into the plate reader. And here the phosphor plate is extracted and scanned with a helium neon laser, imparting enough energy to the electrons to enable them to exit the color holes. Upon their return to their original location, blue light is given off in proportion to the intensity of the X-ray radiation reaching the plate during exposure. The emitted light is captured with an optical array, and a photomultiplier tube amplifies the signals. I'll see if I can point these out, but you know how dodgy my laser is. Yeah, it is. So that's the laser here with mirrors, and that causes the electrons to go back down to their normal state, releasing the blue light, and this is collected by this system here, and the plate is going into the machine here and being read, and these are rollers moving the plate, and the laser beam is scanning backwards and forwards very, very fast. And then all those signals get sent to the photomultiplier tube, which amplifies the signals, and then they're digitized with the analog to digital converters, the ADC, which is at the far right. And the ADC performs three operations in conversion to a digital signal. So you get scanning, quantification, and binary coding. So the one drawback, in inverted commas, to the system is that it's quite time-consuming procedure, taking 30 seconds or more. Wow. But nowhere near as slow as the quickest automatic wet film processor of 4 or 5 minutes. The residual image is then erased from the plate by an intense ultraviolet light source, which returns all the electrons to their original state, and this makes the plate ready to be used for new exposures. And then the central processing unit, so that's the, see if my pointer works there, that's the central processing unit there, controls many of the operations of the system. It receives the binary coding from the ADC and can send it either to a data storage, laser images, which are used to laser print a hard copy of the image onto special film, or to high definition monitors. Modern computers, though, have all the necessary processing power to handle large amounts of data quickly and the capacity to store the images. And you can see I've just blocked out in red 2 of the stages are now no longer required because computer graphics cards are able to send direct digital signals to modern digital high definition computer monitors. So you don't need analog converters and video amplifiers anymore. So this system was used where I was working until retirement. I think the latter is an optional extra. This was a cassette reader, and you'd stuff the cassette in at this end, and the cassette itself didn't go in there, but the plate inside it went into that slot, and all that processing took place inside that machine, which you can see just fits on top of a table, and the end result is on the computer screen here in about 30, 40 seconds. Pretty good. But then along comes digital radiography. That came into operation towards the end of 1998 and is now increasing in popularity. The major benefits of being able to produce an image of wide dynamic range in 3 seconds. Wow. And exposures every 6 seconds. Even more wow. The elimination of the cassette handling and being able to display a preview image immediately, ability to easily manipulate the resultant digital images and share them over a network. Only a few exposure settings are needed, no matter what is being imaged, as this method is far more forgiving than wet film processing. But the present drawbacks of these systems are size and cost. I think a digital system can be up to £300,000–500,000. But it's offset by savings in time, processing, storage of images, and those images are permanent, they never degrade, unlike wet film, non-computerized systems. But one potential disadvantage is that the detector plate is permanently connected to the computer by a workstation, sorry, the computer workstation by a cable. Anyway, let's see how this system works. The system converts the X-ray photons to a digital signal without the use of the intermediary, the phosphor plate, saving time, energy, etc. And we saw the diagram of the direct digital chain earlier, and there are many similarities between this and the computed radiography chain, but the main difference is at the start of the chain and how the image information is obtained. And it's either by indirect or direct X-ray capture. And we'll look at the indirect detectors first. So indirect detectors captures first converts the X-rays into visible light, which uses phosphors either made of thallium-doped cesium iodide or gadolinium oxysulfide. The light photons produced are then converted into electrical signals by the detector of one of two types. So this is the first type, the charged coupled devices. And actually this is out of date now, and I'll tell you why in a moment. But the charge coupled device is a relatively cheap type of detector compared to the next type. It's light sensitive sensor for recording images and consists of an integrated circuit containing an array of linked or coupled capacitors. It's a common and proven detector technology, and it's found in mobile phones, video, and digital cameras. These are the older type. A charge coupled device detector is at its best when a single chip covers the whole area to be imaged, and the total detector area is limited by the charge coupled device detector size. So about 10 years ago, these devices, CCDs, have been replaced by CMOS, which are complementary metal oxide semiconductor sensors. And those are the digital imaging devices that are going to be found in your modern mobile phone. And those have replaced the CCD in this image on the left. The next type is an amorphous silicon flat panel detector. And this indirect conversion digital radiography system is a sandwich construction consisting of a scintillator layer of an amorphous silicon photodiode circuitry layer and a thin film transistor array, or TFT array. So when the X-ray photons reach the scintillator, visible light proportional to the incident energy is emitted and then recorded by an array of photodiodes and converted to electrical signals. And these charges are then read out by a TFT array to generate the X-ray image. So the direct digital radiography detectors are made with amorphous selenium. The amorphous selenium detector plate replaces the scintillator and converts the X-ray photons directly into electron-hole pairs. The detector is manufactured using the same process as for an amorphous silicon detector, but it is simpler in design because it does not need a photodiode layer. Direct capture is very efficient because the X-rays are not converted into light, but directly into electrical signals by the thin film array. So that's the how the display at the bottom is how that works. So the scintillator has disappeared. Here are some images of direct and indirect digital radiography plates, and I can't tell you whether they are direct or indirect digital. It's difficult to say which of these plates fits into which category, but they all do a very similar job of converting X-rays into images. And then this is a cutaway of a dental direct digital plate, which measures only about 2.5 by 4 centimeters, so you can get it into your mouth, and shows the complexity of these devices. I don't know whether my laser pointer will work. Yes, it is. There we go. Those are all the sort of layers of crystals that receive the X-rays, and then that's the device that sends them off to the computer via the cable. So this is our final visit to our requirements slide. We've covered the X-rays and the X-ray generator. We've looked at how we can trap the X-rays, which make up our diagnostic image. And finally, we're going to see how we can make sense of the collected image. For the non-computerized photographic films, we have the light box and magnifier. And for the computer-generated images, we need nothing more than the high-definition computer monitor. Most of us will remember, I'll just go back to my previous slide. If it will, there we go. Most of us will remember a medical drama on the TV where the doctor picks up an X-ray film, places it on a light box viewer and gazes at it with expert eyes while the patient looks on in nervous anticipation. Now, these are still in use, but newer ones have replaced fluorescent lighting with LEDs. And this is our light box. But when fine details are required to be seen, then the magnifier comes into its own. And that's a magnifier and a bright light source. So digital image viewing and manipulation. So this is by DICOM, Digital Imaging and Communications in Medicine. And DICOM is a universally accepted computer-based archiving and image manipulation system. DICOM files contain not only the image taken during the examination, but also embedded information such as details such as the patient's name, the date of the examination, the place of the examination, the physician in attendance, and if you want, you could even put what the weather was like. Images can be copied, edited, manipulated, and new series can be created. Acquiring, copying, and exporting these images can be performed without any loss of information in the DICOM format. Images can be zoomed, panned, annotated, cropped, and crucially, they can have their grayscale adjusted by using zoom and adjusting brightness and contrast. It is a simple matter to amplify and highlight any areas of interest that may conceal abnormalities. DICOM allows full utilization of the 256 grayscale settings available on your computer monitor. And as mentioned earlier, digital radiographs are less critically dependent on exposure factors, as some post-processing of the image can be used to correct for less than perfect machine settings. I'm going to hopefully demonstrate this in a minute. DICOM files can be burnt to CD or DVD or other external storage device. They can be printed on DICOM or Windows printers. They can be sent or exported. DICOM images can be compressed into different file formats such as bitmap or JPEGs and sent by email. And nowadays, cloud storage allows for sharing and downloading complete series of images, despite the large size of these files. So it's not quite the end, because if this works properly, I'm going to try and share my screen in a different way and show you a DICOM program with some x-rays that I took myself years ago. So I'm hoping this works. Help me here if I can't switch my screen. Simon, let me just see. Let's see, new share. Let's try that.
I'm sure you can
Tell me if
do
it comes up on your screen.
It's
Yes,
not there
no,
yet.
not there yet. Okay, still. Okay, what I think I might do is to stop the PowerPoint, and then I shall try and screen sharing has stopped. Not to worry, and we'll try and. Oh, where's my Zoom gone? Here we go. Right, let me just see, share my screen, and let's try that, and let's see if that will work. Okay, can you see that?
Yay, we got it. Well done, Alan. Yeah, we've got
Good.
it.
Okay, now I'm not sure whether this is going to work very well. So this is a DICOM software program, and you can see on the top here. Can you see my mouse pointer or not? No.
Yes, yeah, we got it.
You can.
Yeah,
At the top here, there's several different X-ray sets from different clients, different animals, and different images. Okay, so you can load up as many as you want. If you can, and then you can select the one you want to play around with. So here's an X-ray here. It's not a very brilliant view. I'm going to see if I can change the color on there. Well, not the color, the contrast and the. Sorry, I've got to work out which way to go with my mouse. There we go. So you can see that's changing the brightness and hopefully the contrast. Now that looks a bit better, doesn't it? Compared with the original. So keep a watch and that will see the difference. If you want, you can have it black on white. Okay, so that's a little bit like Röntgen's first images, the negatives. You can do all sorts of clever things. You can, I don't know whether this will work, you can sort of draw circles or check angles. Let me see if I can measure an angle. So if I go, let's see, from here down to, no, it's the other way around. I think I need to go, don't I? Hold on a moment. Let's see. Yeah, there we go. That's measuring the angle at which the hip fits into the socket. Okay, it's one of the ways of checking for hip dysplasia, because if you move this bit of the ball out, this angle would change and become less acute. So as I say, there's all sorts of different ways you can play around with these images. You can drag them. You can show everything at once if you want. So let me see. We'll have 4 views, shall we? And put all the views on. There you go. See how simple it is? Try and do that with film. There we go. So we've got a left leg and a right leg here. Both. This is a front leg of a dog, and I've flexed the elbow. That picture's not very good, is it? Let's see if we can change the brightness of it a little bit. There we go. That looks a bit better, doesn't it? Can you see a bit more detail on that?
Alan,
And,
what's the L and the R?
that's left and right.
Oh, right. Okay. Got you. I was trying to work
Okay.
out what. Yeah. I was trying to work out if they swallowed something.
There you go. It tells you that.
I got it.
No. So this is the foreleg, the elbow. This is the
Yeah.
sort of the shoulder up here.
Yeah. Got it.
Okay. And this is a bit of the chest bone here.
Got
There
it.
we go. What else can we do? Trying to think now. Yeah, so on this, I'll close this bit. You can, all sorts of detail is present here. Let me just get rid of this. Oops, no, that's not what I want to do. Hold on, come back again. I'm trying to actually, I've got the Zoom meeting information in my way here a little bit. So let's try and, that's better. Let's try and just move this out of the way. I'm trying imaging tool. You see there's lots of menus here. You can rotate images. Can you see that rotating underneath the selected one? I'll switch to that one there and you'll see that. So there's all sorts of things you can do. Rotate. Okay, turn it that way around if you don't like it that way around. You can zoom in. So if you don't have your magnifying box anymore, I'll see if I can move the image. No, I can't move the image here. Let me just see. Nope. Okay. I'm not used to this program, by the way, so that's why I'm sort of playing around with it a little bit. But you can actually pan and move the image around if you pick the right setting. Let's see what's on the display here. No, that's not. You can anonymize. You can see how the information gets switched off. So if you wanted to send it away anonymously, you could just click that. We can see how much information is embedded on those X-rays. So that's sort of a very brief overview of DICOM. I'll show you this one. This is a dog where I was going to, let's do 2 views, 1x2 views. And then this is the beforehand. Let's see if I can just, no, I can't. Let's click this. There we go, a bit better. Okay, this is one I was going to, this animal had a problem with its knee, and because of the angle of this plateau here was too steep, and we can actually measure that angle. And what we were going to do is chop a little bit of a wedge out of its bone and join them up with a plate, and that would then flatten this angle out a little bit more. And so you can see all the measurements that are on here. And so if I zoom in, you can see those measurements which I've taken on a different DICOM viewer system, and that's the size of the wedge that I've got to chop out. And that's the angle here. Where is it now? 31.93 degrees is the angle of that plateau compared with the axis of the leg, which you can see a line going up here. So anyway, I think that's enough because I'll baffle you with science. So I'm going to try now just to go back to the PowerPoint, and so I need to new share and do the PowerPoint, and we'll finish off if I can. I'm not quite sure what I'm sharing. Oh, I'm sharing the whole thing. Let me just go to the Shift F5, and then that should finish off. Right, okay. There we go. Because I must acknowledge some of the people who've helped me to put this together. There's Wikipedia, of course, and all those who contributed to it. There's some Veterinary Times articles, and everyone who's shared relevant images on the internet, and there's far too many of them for me to acknowledge all of them. But this guy, Vishal Sangpal.
Alan, I think your screen's not sharing, or it is sharing, but it looks like it's frozen. Can't see your mouse moving anymore.
No, okay. I'm not. Well, I was pointing out, but can you see the acknowledgement?
No, it just says not quite the end. It's still your
oh, right. Okay. let's.
That's okay. Just read them out.
What are you seeing now?
Still not quite the end. It's still your slide sorter.
Oh, it's frozen, has it?
Yeah.
Okay.
Yeah.
Oh,
Yeah.
let me see. If I stop sharing and then start sharing
Yes.
again,
Yeah, try that.
and I'm just going to put my mouse back again, my program back again. Otherwise, well, no, I may as well just share what's on it. And let's see, share that, and go back one slide, because I need to finish the.
There we go. We got it.
Good. So that's the acknowledgements. Can you see that?
Yeah, got it. Yeah, we've got it.
Brilliant. You probably won't see my mouse. So the one at the bottom there is, I was just going to credit Vishal Sangpal, radiology resident at the Nizram Institute of Medical Sciences. I don't know him, but he did have a science slide presentation and told me how digital radiography works. Otherwise, I wouldn't have a clue. So thank you to Vishal, whoever he is. And I shall now say, I think we have had enough. Any questions?
Thanks, Alan. Absolutely superb. Thank you again. Thank you.
So I will try and stop sharing my screen if I can. Oops. Well,
Okay,
you've
that's
done
it. Yeah, we got it. We got it. Wonderful. Alan, that was absolutely fascinating. Anybody got any questions?
Sorry, you're breaking up, Simon. I don't know whether that's me or what, but I can't hear you.
Okay, you got me now?
Yeah, yeah.
Okay, super. Thank you, Alan. I was just saying that was brilliant. Thank you. So fascinating, so interesting, and such a depth of knowledge there. And very honest at the end, I must admit.
Yeah.
The important thing is acknowledging what we don't know and going and finding out about it, isn't it?
Oh, yes.
Absolutely. The sign of a true professional. True professional. Okay, anybody got any questions? Anybody got anything?
It's as much an observation. It's those people in the early years doing the X-rays, how they found out that they were harmful. I suppose they found out the hard way, did they, that they were harmful? Because at first they wouldn't have realised. Yeah. Imagine the parties having all pictures of what can we take a picture of now? You know.
Yeah.
Well, Sue and I both remember going into shoe shops and sticking your foot inside a machine to see if the shoes fitted. And you could see your, I remember it being done when I went to Germany, to Berlin, when I was 6 years old, 1961. So you can work out how old I am. Yeah, I remember looking down into this viewer and seeing the skeleton of my foot.
Yeah.
Really?
And of course, yeah, I don't know whether these things were safe or not, but I don't think I've suffered any.
But they would have known by then, wouldn't they, that it was harmful? So they would have known by then that it was harmful. So I wonder if they just went with such a low dose that they didn't think it would have any effect.
I don't know. I think obviously the one-off X-ray, I mean, you know, is not going to cause you too much damage. But obviously these experimenters didn't have a clue what they were doing, and you know, and thought this is amazing, you know, and they just thought of it like photography.
Yeah,
there's no hazard with photography, is there? I can point a camera at you, Simon, and you won't go radioactive.
Yeah. I mean, it's not like sticking your face on the photocopier, is it? It's kind of it's more of a dramatic effect than that one.
Yes.
Wow, absolutely amazing. But so often, isn't it, with these people that that they did these experiments and not knowing what the impact was going to be? I mean, they must just have been amazed that they could see these things.
Yeah.
Fascinating. So, Alan, when is there ever an occasion when you've been faced with I don't know, an injury or something that you've got to take a picture of, and you just can't get the correct angle or the correct image in to be able to take that picture, or something blocks it and you can't work out what it is blocking? You know, is it sometimes, I guess what I'm asking is it sometimes impossible to get the picture that you want?
Well, you can imagine something like a horse trying to do an chest X-ray of a horse.
Yeah. You can't say just lie there still. Can
Well, there aren't any X-ray cassettes big enough.
Yeah.
So you would probably have to take lots of them, and you couldn't do that with photographic film.
No.
Whereas with nowadays, you could probably take lots of X-rays, and as I say, with direct digital, you can take one every 6 seconds, and the computer will stitch them together for you.
Yeah.
So, but I don't know how they do it in horses. They obviously do.
Yeah.
I showed a picture of them photographing X-raying a horse's hoof or foot. I mean, I've done that in the past, and that's feasible. But again, they are not the most patient of creatures, and if they kick out and damage the equipment, and especially if it was a direct digital system, that's probably about 30, I don't know how much a digital plate costs, probably £1,000 or more. So certainly the technology is getting cheaper nowadays. But as I say, a direct digital system in a hospital it's 300,000.
Yeah. Wow.
Yeah, a lot of money. Yeah.
But
yes, positioning can be difficult. I mean, you imagine trying to take a view through the back of a dog's hind leg.
Yeah.
Okay, it can be done.
Yeah.
But really, they have to be anaesthetized.
Yeah, of course. Yeah.
Because you're putting them in positions that no normal dog would let you put them in.
Yeah.
And if they're a bit sore, they wouldn't like you to do it anyway.
No, of course not. Of course not. Wow.
So anesthesias or sedation or good quality pain relief is essential.
Yeah, absolutely. No dog whispering there. Just
no.
Excellent. Any more from John? It's lovely to see you. Great to see you, John.
Hi, John.
You're looking well. John, you're muted at the moment, so I think you have to unmute.
Yep.
Yeah, we got you.
Yes, I'm
Nice to see you.
I've got a mic.
Happy New Year.
I haven't had a CT scan since yesterday. I speak as an expert. The direction it took was across here, just to include my ear cavities. And it was just that. So I had to take my teeth out, take my specs off, take my hearing aid out. It was quite a palaver. But it was to reveal if I'd got a problem with the right ear, which is cholesterol granular. And obviously they can zoom in on that and have a look at what's happening in the cavity, because it couldn't be seen normally. The other funny thing is, 6 years ago, I had a stent, and it went up through my trouser leg, up through the groin, and the stent was fitted into the aorta, which I was able to watch on telly, which is quite interesting as well.
Yes, yes.
That was obviously pretty expensive stuff, but it was all in real time. Yeah. And when the stent went in, the consultant said, stent inserted successfully, at which point a whole lot of people in the room were all cheering like mad. It was rather like a space launch.
Wow.
Now you see, if that was Star Trek, it would all be done by sort of magic.
It was magic.
Well, so much has come true from Star Trek, Alan, hasn't it? You know, it
has.
The iPhone, there it is, the iPad, all of that stuff.
Yeah. And that's probably the subject of my next talk, what John was just mentioning. When that'll be, I don't know. When I've recovered from this one, I guess. But yes, tomography and computed tomography will be the next subject. But that's still X-rays. So
super. Yeah. Has anybody got any other questions? No. Okay.
I've baffled them all.
Well, Alan, I want to say thank you for this evening. It's been excellent, particularly you had such short notice to put that together. That was excellent. You know, you only had a week, 2 weeks notice at the most.
2 weeks.
And then it was uncertain whether it was going to be you this month or next month. So thank you so much. That was a wonderful way to spend an evening. and we do appreciate it. And of course, the recording will be available online as well shortly. And then we'll be back with you on the 17th of February. And in the meantime, no doubt Alan will be preparing the next part of the talk, which we will hold him to get that done, because now you've whetted our appetite for imaging. So
give me a few months off.
I don't know about that. We'll have to have a word. Anyway, listen, thank you all for joining in this evening. It's great to see you all. Thank you for joining us on YouTube as well, and we look forward to seeing you next month, hopefully face to face. And once again, Alan, thank you for a marvelous talk. That was absolutely excellent.
That's okay. Thank you.